Yes, I made a mistake. Mr. Seamon makes mistakes. Yes, I did make a mistake. I did make a mistake, yes. Other questions? Any other questions about VARD? Yes?
Is it possible to do with the Quadratics?
Yeah, no, the question, is it possible to work with higher order polynomials? That's a good question. What other questions do you have? Other questions, yeah.
Like, I didn't really understand the removable discontinuities.
Yeah, what the heck is a removable discontinuity? Other questions? Any other questions at all? Any other questions? Nothing. No other questions? Okay, that's fine. Simply means plugging a value in and getting out an output. That's it. We are particularly interested in values of x that result in the polynomial equaling what? We're really interested in values of x that when you plug them into a polynomial, the polynomial equals 0. You've literally done that hundreds of times. Mr. Seamon makes mistakes. Find them and tell me about them. Okay? Find them. Is it possible to work with higher order polynomials? Now this really is the key question. What is the answer to this? Yes. The method I'm teaching you will apply theoretically to any polynomial. Does that mean you're going to be able to do it easily on any polynomial? No, but it'll at least give you a place to start. What's your fail-safe for working with quadratics? Yeah, you could factor, but your fail-safe is you can always use what? Quadratic formula, quadratic equation, quadratic formula, quadratic formula. You can think of this method as the quadratic formula of these higher order polynomials, except for, is there a cubic formula? What do you think? If there's a quadratic, is there a cubic? Yep, there is. Quartic, fourth degree? What do you think? Yep. Quintic? What do you think? Nope. This is a really, really fascinating lesson in mathematics. There is a cubic, there is a quartic. There's actually many others that are higher than 5. But you know what's really interesting about 5? It's not that it hasn't been found. It's that in multiple different ways, people have proven that it does not exist. First part of your homework, bring in the cubic equation. Just want to see what it looks like. Bonus, bring in the quartic. Okay, let's talk about this. What is a removable discontinuity? Can anybody tell me what a removable discontinuity is? What is it?
Well, it's a value that seemingly exists according to the simplified version of the function.
The function passes through the point when it's most simplified.
Yeah.
That's one way to say it. It's not totally correct, but that's the best communication. I like that.
Actually, it doesn't do this domain.
Exactly. But the domain prevents the function from being defined at the point. Simply put, it's an open dot. That's all it is. And we're going to talk about that in more detail in a second. Were there any other questions about VARD? Is everybody going to, maybe we'll have a higher percentage of people that see the video this weekend? What do you think? Yeah? I mean, I have about 4 quizzes I'm going to give back to you on Monday. And it's going to start hurting a lot if you get zeros on quizzes, kids. Just throwing that out there. Any other questions? And I realize you don't have that many because half of you didn't actually watch the video. That's okay. Okay, let's move on then. You had to do, as part of your homework last night, you had to look at R4. Let's take a look at R4. Here's R4. What was your reaction to working with R4? What was your reaction to working with R4? Do you remember? Hard to factor. Is it factorable, though? Is it nicely factorable? It is. It is. Isn't it? Can anybody tell me what the nicely factored form is? What's the numerator? Anybody have it? Anybody have the numerator? Pang, what is it?
2x minus 3.
Yep.
And 3x plus 1.
3x plus 1. And Jonathan, do you have the bottom?
The bottom is x minus 2, 2x minus 3.
So if we did work through DIS, which we know as domain, intercepts, and symmetry, what's the domain of this function? Someone raise their hand and tell me. What is the domain of this function? Claire.
X such that x equals not 3 halves or 2.
Doesn't equal 3 halves or 2. Correct. Does not equal those things. So it's all real numbers except those things. Intercepts. What's the easy one? The y-intercept when x is 0. When x is 0 on this, what does y equal? Negative what? What? Negative 1 over 2. So negative a half. Yep. Now, what about the x-intercepts when y is 0? What makes this? How do you make a fraction equal 0? Numerator is equal to 0, right? So we know it's equal to 0 when what is true? When x is equal to? Negative 1/3. And what's the other one? 3 halves. Let's just pause here for a second. What's a problem? What's a detail that we need to see at this point? Look at this. You see that point right there? Is 3 halves part of the domain? No. Is that therefore an x-intercept? Nope. It's not, because it's not part of the domain. So how many intercepts does this function have? Has 1 intercept. No, has 2. Has 2 intercepts. Has 2 intercepts total. 1 x-intercept and 1 y-intercept, yes. Has 2 unique intercepts. What about symmetry? Did anybody test symmetry on this thing? And it's what? Neither, yeah. That's not super helpful, but it also means that you know there's no mirror image, there's no rotation around the origin. So let's work on VARD. What's VA stand for? Yeah, vertical asymptotes. Yes. Vertical asymptotes. What do you have to do first before you find the vertical asymptotes? Simplify it. Why were these steps so easy for us to do? We had done this type of work previously, but what setup work had we done to make those steps really easy? We had factored. I said something in the video. I love factoring and? Anybody remember? And so will you. I love factoring and so will you. In factored form, are these questions much easier to answer? Sometimes if you don't factor, you won't be able to answer them at all. So now we simplify. What cancels? And we're left with a new function. We'll call this R. Is this R3 or R4? This is R4 simplified. 3x plus 1 over x minus 2. What's the domain of this function? X such that x 2. Whatever the hole in the domain is in the simplified form, that means the vertical asymptote at where? Where is the vertical asymptote? It's at x equals 2. You have to write x equals 2 because this is a vertical line. If you just say 2, is that enough information? You need to say x equals 2. Are there any other vertical asymptotes? Hold on, wait. Are there any others, do you think? There are no other ones. But there's something that goes hand in hand here. RD, the removable discontinuities. How many vertical asymptotes could you have on a function? You could have an infinite number. How many removable discontinuities could you have? Give you a hint. There's only 1, 0, or an infinite number. You can have as many as you want. Are you guaranteed to have any of these? No, you can have 0 of each. But what you do to find a removable discontinuity, do you remember from the video what you need for a removable discontinuity? you look at what you canceled out. Whatever you canceled out is where the removable discontinuity occurs. So where does the removable discontinuity occurs? At x equals 3 over 2. The removable discontinuity happens at x equals 3 over 2. What that means is, here's x equals 3 over 2. The function is going to be traveling along, doing whatever it's doing. When it gets to 3 over 2, it continues on its way. What's the only thing that happens? What is that? It's an open dot. The function is defined everywhere else except at that open dot. Does the function do anything crazy like this? No. If it did, what would that be called? A vertical asymptote. You can't have something be a vertical asymptote and a removable discontinuity. A removable discontinuity is a point. A vertical asymptote is a line. Can they be the same thing? No. So the real question is, okay, we know it occurs at x equals 3 over 2. We'd really like to know not only the x coordinate of that open dot, we'd also like to know the what? The y coordinate. The problem is, if we go back to the original equation, can we plug in 3 over 2 into that equation? No. What happens if we do? We end up with a dividing by 0. Different kind of imaginary. We can't plug it in there, but where can we plug 3 over 2 in? The simplified form. You take this and you do R4 simplified form of 3 over 2. And that's equal to 3 times 3 over 2. Is it plus 1? Yeah. Over 3 over 2 minus 2. Can we plug 3 over 2 into this one? Yeah, we can. Why can we? We specifically eliminated it. Structurally, what's the difference if I graph this and if I graph this? What's the only difference between the two? There's only one point that's different. The what? Yeah, the point I erased. So this function travels along, and you see how there's an open dot there? By simplifying it, what did I do? I filled it in. By simplifying it, I filled it in, meaning, can I now evaluate at 3 over 2? Yeah, so if we do this out, we end up with 9 over 2 plus 1 over negative a half. That's equal to 11 over 2 divided by negative a half, which is equal to 11 over 2 times negative 2 over 1. What's that equal? Negative 11. So there is an RD, a removable discontinuity, where? What's the exact location? 3 over 2, comma, negative 11. That's where the open dot is. Is the function defined there? No. Huh? No, that cancels. What? It's negative 11, isn't it? That's 11 over 2 over negative a half. Dividing by a half, you flip it over, right? We're good? Okay, so that's where the removable discontinuity occurs. Is there an asymptote there? Can you have an asymptote where a removable discontinuity is? No, you either have a vertical asymptote or a removable discontinuity, or the function's fine. Has everybody graphed this function before? This is not a trick question. Have you graphed the function y equals x? Yes. You have? Okay. What happens if I graphed this? What happens if I graph x times x plus 2 over x plus 2? I mean, I can multiply it out. You end up with x squared plus 2x over. Now, that looks a lot more complicated than y equals x, correct? Anybody want to guess what the graph looks like? It's the exact same thing except what? There's a hole at negative 2. There's a hole. That's the only difference. That's the only difference. Why? X plus 2 over x plus 2. If I plug in any number besides negative 2, what does that equal?
1.
It equals 1. When you multiply 1 by anything, what happens to that thing? Nothing. Stays the same. So what are we doing? When I add in x plus 2 over x plus 2, am I changing anything? No. All I'm doing is creating a hole. All I'm doing is creating a hole. So for example, let's say I gave you this. I like using this little tiny eraser. Let's say this green function is originally y equals x. Can someone just tell me what this new function is? What do you think f of x is? Someone just raise their hand and tell me what it is. Tell me what it is. I know you guys can do this. Salmon, what is it?
Is it f of x
Equals
equals x, but the domain
times what?
Plus 3 over
X plus 3 over x plus 3 times
x minus 4
times.
minus 6.
So if I multiplied this out, what would what is that type of function? What is that called? Nope. Nope. I agree with it. A piece of that function is a quartic, and a piece of that function is a cubic. What is this function called? What type of function is it? Yeah, eventually, but what's it called right now? What types of functions are we dealing with? Are you even dealing with for homework for tuning? Oh, there it is. Sorry, possessed for a second there. Rational function. If we multiply this out, it would be a quartic over a cubic. Would you automatically recognize it as y equals x? If I multiplied it out, could you just look at it and know? No. If you really wanted to, could you multiply this out by hand? Sure. It's kind of annoying, right? Easy to make a mistake. Could you multiply this out by hand? Yeah. What happens if I gave you the multiplied form and I said graph this? What would you need to do first? You'd have to not multiply. You'd have to, if let's say I gave you the multiplied form of this, you'd have to factor it. Multiplying, easy. Factoring, hard. Right. So here's the thing. We now have this. DIS-VARD. Domain, intercept, symmetry, vertical asymptotes, removable discontinuities. They tell us a whole bunch of different little things about the function we're trying to graph. The whole process is made possible. The whole process is made easier if you can what? What do you need to do to the rational function? Why are you factoring? You want to simplify, but to simplify, you need to be able to factor. If you can't factor, you're going to have a very hard time simplifying, meaning you're going to have a very hard time. If not, it's impossible to tell me almost any of those. So what do we need to get really good at? Super, super important. You need to get good at factoring. Are you ready to practice some factoring? Sure. We're going to take a little pause because I want to show you, give you a little palate cleanser. And the other thing is I put those videos, I created a document called Precalculus videos, and in the document are links to the videos that I'll show. So if you want to see them, they're in your class documents folder. We need to talk about something really, really important, which is the key to this whole process. We've decided that we need to be able to simplify these polynomials. We need to simplify them primarily through factoring. And what's our big tool going to be in terms of factoring? There was a two-word phrase, two-word thing. Synthetic division. Exactly. Synthetic division. Synthetic division just evaluates polynomials. That's all it does. You evaluate polynomials. It's really helpful because you want to know when the polynomials equal 0. This method helps you test potential zeros and then narrow the list down. So let's start with this. Have we seen functions that look like this before? What is that? Quadratic. Factors into x plus 2 times x plus 3. And what does that look like? Well, looks like a parabola. -2 and -3 and a upwards facing parabola. We good with that? I'm pretty happy with that. The numbers -3 and -2 are called what of the original polynomial? They are what? They are zeros. They are x values, but they are zeros. What are these called? X plus 2 and x plus 3. What are those called of x of the original polynomial? They are factors. Do you notice a correlation between the zeros and the factors? This 0 correlates to that factor. This 0 correlates to the other factor. If you know a 0, what do you automatically know? A factor. If you know a factor, what do you automatically know? a 0. So factors, knowing a factor and knowing a 0, it's pretty much the same thing. Agreed? So if you can find all the zeros of a polynomial, what have you effectively done? Exactly. If you know all the zeros, you know all the factors. So let's look at one of the polynomials we're going to have to work on for homework tonight. Let's look at 5. So if we look at 5, we'll throw this VARD at it. But in order to throw this VARD at it in the most economical way possible, at some point we're going to need to what to each the numerator and the denominator? We're going to need to, because I love factoring and so do we, right? So I think that'll be our call response. I love factoring. There we go. If you say it enough, maybe it'll come true. Numerator, denominator. Which one do you think is easier to factor? Why? Smaller numbers. Smaller numbers. Smaller numbers. Yay! Smaller numbers. We love smaller numbers. Awesome. So we want to know when x cubed minus 4x squared plus x plus 6 equals 0, right? Cubics either have 1 or 2 or 3 real answers, real zeros. You could either have a cubic that looks like this. How many times does that cubic cross the x-axis? So it has 1 real 0. How many times does this one cross? 3 times. What about this one? 2. So you can either have 1, 2, or 3 real answers. Let's say you figure them all out. Let's say there were 3 of them. Let's say the 3 zeros were R1, R2, and R3. If these are zeros, what do the 3 factors have to be? X minus R1, X minus R3. If you multiply them all together, what do you get? The equation. There might be a coefficient out front. There might be a coefficient out front, but the really important part, did you get most of it? Yeah. So here's the key, though. If we're going to analyze the bottom function here, x cubed minus 4x squared plus x plus 6, we want to know when that's equal to 0. Because if we know when it's equal to 0, we know what all of the factors are. The problem is, do we have a place to start yet? I told you about it a little bit last night in the video. Right now, could we just pick numbers and throw it at this equation? We could. How many numbers are there? There's a lot of numbers. We want to take that list and shave it down. I told you about something last night called the potential. Do you remember this? Some of you? Rational zeros theorem. Potential rational zeros. We're going to make a list of the potential rational zeros. What does that mean? It means exactly what it says. These are potential rational zeros, meaning do they have to be all zeros? No. If this thing has rational zeros, they will be in this list. We're guaranteed to have at least how many? Actually 0, because you see these numbers? Could that be like negative square root of 2? Sure. Is root 2 a rational number? No. So you're not guaranteed to have any of these work, but if there are any rational zeros, they will all be in this list. Do you remember how you make this list? You look at the number 6, and you find all the what? Yeah, all the factors. What are all the factors of 6? 1 and plus or minus, right? You also look at the leading coefficient right here. What is the leading coefficient right there? 1 is your friend, because what are all the factors of 1? To make the list of potential rational zeros, you take all of the ones on top and put them all the possible numbers down here. You start pairing them up. 1 over 1, 2 over 1, 3 over 1, 6 over 1. So, what is the list of potential rational zeros? Plus or minus. What would happen if instead of 1, this number was 4? How many factors are there?
1, 2, 4.
1, 2, 4. Does that make our list longer?
Yes.
Makes it much longer. But now, how many potential rational zeros do we have? How many are in there? Now that seems like a lot, but guess what? Is that a lot? How many did we have to start with before? What did we narrow it down to before? Infinite. So we just went down from infinite to 8. Is that a pretty good drop? Yeah. Overall, when you do these, having 8 is going to be about average. That's good. Will I give you things that have way more than that? Sure. Are you ever going to have to test all of these zeros? No. Again, if you watch these videos, this is a lot quicker. You test, if all of these numbers have an equal chance of being zeros, which ones do you want to test first? Small and positive. So what number should you always start with? Always start with 1. You start by writing the number you want to test right there. You don't have to circle it, but I am. You take all the coefficients. What are the coefficients of that polynomial? And you make this little L bracket. The first step, so this is the number we are testing. Remember, what does synthetic division do? It just evaluates the polynomial. That's it. And gives you some other cool information. First step is always drop this number down. Now you multiply by what you're testing. What are we testing? So we multiply by, and now we add and repeat. Multiply by 1, add, -2 and 4. What does this tell us? It tells us that f of 1 is equal to 4. So is 1 a 0? So x minus 1 is not a what? It's not a factor. We just tested 1 and it's not a factor. Do you erase this at this point? No. Please keep track of what you test. I see this happen all the time. Kids do this, they erase it, they do it again, they erase it, they make a mistake, and they don't know where. You will get a sense of what you should test next. What do you want to test next? Let's try 2. You know, if they're all the same, let's try 2. You do the exact same thing, but with 2. What were the coefficients? You drop 1 down, and you get 1 multiplied by 2. And? Is that what you're looking for? You love that, because that tells you that f of 2 is, so x minus 2 is a. This tells you, at this point, you stop, you pause. Do you keep on testing potential zeros? No, you pause. You've now found one factor, and this is very helpful because it tells you that x minus 2 is a factor, multiplied by something is our original polynomial. Do we have any idea what that thing is? If you watched the video, kids, you'd know the answer to this. It's already on the board. The cool thing about synthetic division is it tells you what the other polynomial is. This is the constant, this is the x, and this is the x squared. So what goes in there? 1x squared. What type of polynomial is that? Have you dealt with quadratics before? You are home free. You might be beaten up and bloody, but at this point you've made it home. Is this nicely factorable? It is. X minus 2 times x plus 1 equals the original polynomial. So did we just factor the numerator? Sorry, the denominator? We did. To continue on, what would you have to do next? We just factored the denominator. We need to factor the what? Numerator. What was the numerator on this thing? The numerator was 1, -6, -130. 1, -6, -1, and... So we're happy there, but we want to factor that. Right? What two numbers do we need to look at to generate our list of potential rational zeros? 30 and 1. What are all the factors of 30? Plus or minus 1? And A, is 1 your friend again? Yeah, so your list of potential rational zeros is right here. Is that more? Yeah. Hopefully you get lucky and you find one, because once you find one, it goes from a cubic to needing to factor a quadratic. And do you have tons of experience factoring quadratics? This is where sometimes if we have time, I'd give some of you some of the rational zeros, and some of you, as a class, we would test a bunch of them. What are the coefficients of this polynomial right here? 1. You would just start testing numbers. What do you start with? You can try 1, eat 1, 1, -5, -5, -6, and -6, and 24. It seems like 1 is too small, so let's try what? 6. Try 2. The point is, once you find 1, do you keep testing? Don't keep testing once you find 1. Write the factored form. Once you find 1, write the factored form, because once you take one thing out of a cubic, it becomes a quadratic. And are you comfortable with quadratics? You should be. You should be. Should be. Should be. Does this method work on any order polynomial? Yeah. Does it get more interesting if the numbers are big?
Yeah.
I mean, think about it. What happens if look on this one right here? What happens if this was like 16? Let's just think about that for a second. Let's say it was 16x cubed plus 20x plus 4x plus, I don't know, 9. What are the factors of 9?
1, 3, 9.
Factors of 16. 1, 2, 4, 8, and? So what are the potential rational zeros? 1 over 1, 1 over 2, 1 over 4, 1 over 8, 1 over 3 over 1, 3 over 2, 3 over 4, 3 over 8, 3 over, and 9 over 1, 9 over 2, 9 over 4, 9 over 8, and 9 over. Would that be a terrible list to check? At least it's better than what you started with, but that's not very nice. It's not very nice at all. Remember, are you guaranteed to have any of these work? No, you're not. Your homework for tonight, you already have one piece of homework. What is the first part of your homework? To find the cubic for me. To find the cubic. The second part of your homework is going to be, and I'll write it all down here, run disVARD on R5 and R6. Run disVARD on R5 and R6. And the last thing is going to be what? Watch Rational Functions Part 3. Is it really important that you watch these videos like I asked you to? Yeah, it is, because you know what? The reason we're going this fast is because if you had watched the videos, you'd be able to keep up.
Don't watch them at night.
Yeah, you might want to watch it while you're conscious. So, you know what the homework is? Good.